Right. Let's see what it's looking like. Yeah, if you have a question, you can feel free to either unmute yourself or you can type your question in the chat. Unless it needs to be private, then we can do a breakout room. Okay, well, so yeah, you can either type it in the chat or let me know if it needs to be private, and I'll make sure that we get into a breakout room. But feel free to go ahead and ask it. In the interim, while we're waiting for that, go ahead. Hello. Okay. All right. Let me see. As far as announcements go, so this is the top of week 5, right? So hopefully everyone had a good weekend. Exam 1 was due last night, so at midnight, so Sunday night at 11:59 p.m. going into this morning. I had an interesting experience with a student in the last session where, he said that his computer messed up. I was able to pull up the records and I was able to see how he did on the exam, and he was like trying to see, if there was any way to kind of get around having to retake it again. And I was like, well, I told him, I was like, okay, I'd be willing to do this. If you can answer the question here on the spot and convince me that you know what you're talking about there, then I can give you credit for it. And I mean, he did enough. He did enough to get,
I DM'd you the question.
Huh? Go ahead.
I DM'd you the question, like I direct message.
Let me check it. But yeah, that was an interesting experience. Book voucher. Okay. Get the student. So with the book voucher, let me let this in. Let me stop the screen share. Let me see. Okay. Okay. Yeah, just be careful about waiting too long to access it. I kind of designed the course where all the assignments have an automatic extension built into them. So even though they have due dates, you can work on any assignment past the due date with only a 10% late penalty. So if you're gaining access late, it's okay. You still get unlimited attempts. But the thing is, the highest you can earn on any question that's submitted late is a 90%. Like I can't get full credit for stuff that's submitted late. I know it's a bit, it's kind of like out of your control, but that's just the way I have it set up. But I think that 10% is, you could still get like a A- with that, and that's on past assignments. But then, you do the best you can with the stuff in the past, and then just going forward, you just try to submit stuff on time, and I think you'll be fine. So yeah, I mean, you're kind of okay. Just be careful about waiting too long, because you still have to go back and like work on everything, and that takes time. With this kind of stuff, you want to avoid procrastination as much as possible. The more you procrastinate, the harder you make it on yourself. This topic is already hard enough as is. So that's why I tried to like have things available early to try to minimize that crunch experience, but yeah, you should be fine. Let me think. So I think I answered the question. And you can use the book voucher to purchase the access code from the bookstore, just whenever those become available. There is an option for like a 2-week temporary code. It'll last for 14 days. So if you think you'll get it within the next 2 weeks, then the temporary thing will be fine. That way you're not just waiting for everything to become available. But that's if you think it'll arrive within the next 2 weeks. Like basically what happens on Pearson, when you go to when it prompts you for payment, at the bottom of that screen is going to be a link that says get 14 days of temporary access. So you can use that to get started on your work, and it'll save your work. But you want to, you do want to try to like gain full access within those 2 weeks. So we had exam one that was due last night or early this morning. But again, we could work on any assignment past the due date. We get unlimited attempts, and the system is set to take our highest score, and there is a 10% late penalty on all assignments. Yeah, I can't think of anything else. Let me check here one more time. Yeah, it's not, as long as you get it submitted before the end of the semester, you can earn up to 90 if it's late. I have not seen that student. Let me share the screen. Oh, there he is. Speak of the angel. Right on time. Okay. All right. Yeah. So I can't think of anything else. So yeah. So in my last session, the student had a question about. I had a student earlier in the morning, and I suggested, I was like, okay, just remind me towards the end of class. And the class came, and I was looking for him. I was like, there was somebody that had a question. I guess he had like dipped out, so he didn't get a chance to ask his question. So the same thing happened again in my previous session, the one right before you guys. And so I was like, well, since this is remote online asynchronous, I was like, they already have a copy of this lecture, so I was like, let's take some time to look at his exam. And I told him, in the end, basically, I was like, okay, if you can like walk me through the question that you missed right now, I'll give you credit for it. Otherwise, what he would have to do, he would have to retake the exam. And every time you take the exam, it gives you a completely different set of questions. Same content, but different questions. So I was like, okay, to try to spare him from having to take the exam again to improve his score, he basically did an impromptu like pop quiz. He did it on the fly, walked me through it. I was like, okay. So for that, and so I'm saying that because if you had worked on the exam and you wanted to try to recover some points, we could do the same thing, right? We could sit down, talk about it. And if you can convince me that you know what you're talking about, I'm open to, giving you credit for that question. So you don't have to go back and redo the whole exam. But even aside from that, if there aren't those kind of questions or concerns, usually, what I do is I'll go through the lecture, right? So this week we're continuing chapter 1 with section 1.4, library of functions. Since we meet twice in a week, what I like to do is on Mondays, we'll go through as much of the lecture together as we can. But again, a recording of this entire lecture is already available on my YouTube channel. The links are usually in each of the descriptions for each video, right? So on Mondays, I like to go through as much of the lecture together as we can. And then on Wednesday, we'll go through as much of the homework together as we can. And so that way we can kind of like try to touch on like pertinent information. So with this section, section 1.4, library of functions, we would like to talk about the following objectives. We'd like to define what do we mean by a linear function, discuss important properties of functions. We'd like to graph square root and cube functions. We'd like to evaluate and graph piecewise functions. We like to graph basic functions and find the average rate of change of a function. Right? So again, we're not going to have enough time to get through all of that in class today. So that's why I made the pre-recorded videos. Can I get a volunteer to read this slide for me?
I heard it. Hello?
Yeah.
All right. So linear functions. Let m and b be real numbers. The function f of x equals mx plus b is called a linear function. If m equals 0, the function f of x equals b is called a constant function. If m equals 1 and b equals 0, the resulting function f of x equals x is called the identity function.
That was awesome. Thank you. So linear functions, right? So that means we're talking about lines. We let m and b be real numbers. Then this is basically y equals mx plus b. It's a linear function. If your slope is 0, then the function, see, like if the slope is 0, this term goes to 0, right? So terms are things that we add and subtract. Factors are things that we multiply and divide, right? So if m is 0, this guy goes to 0, and we're left with f of x equals b, right? And that's called a constant function. So that's like y equals some number that's going to be a flat horizontal line. If the slope is 1 and the y-intercept is 0, then this is like y equals x. It's called the identity function. So it's basically a diagonal line. Okay. And here's a pictorial representation. Man, getting old. You start getting older, you just get these random pains. I'm like, what the hell is that? I'm just sitting here, my body's like aching. I'm like, come on. It's okay. So the graph f of x equals mx plus b. The graph of a linear function is a non-vertical line with the slope m and y-intercept of b. So if our slope is positive, as we trace the graph from the left to the right, it's going to go up. If our slope is negative, as we trace the graph from the left to the right, our graph is going to fall or go down. Okay, I think that's pretty straightforward. If our slope is 0, then we're going to have f of x equals b, which is the constant function. So y equals some number is basically a flat horizontal line. Okay. If our slope is 1 and the y-intercept is 0, then we're working with the identity function. Y equals x, and it's a diagonal line. Okay. So here we asked to write a linear function g for which g of 1 equals 4 and g of negative 3 equals 2. Okay. Any brave soul feel like they can walk me through this one? Oh, another update I meant to mention. So I went on and made, so basically all these notes that you see me writing, I went on and made a copy of these, all the notes that we've discussed so far available on Blackboard. So when you go to Blackboard, there's going to be one of those folders says box link, and there you're going to find a copy of the PDFs that we've been working on. But I went on and dumped a copy of the PDF for all of my College Algebra 1 courses. It's like for you guys. So, but I tried to make the labels pertinent so that, you can find the stuff for your class. And if you want to kind of peek in on another class, you can. Because again, those sessions are streamed as well. And I put all the streams in the same place and I put the PDFs in the same place. So basically with each session, I loaded a copy of like the students' notes in advance. So you should be able to get like these same notes where it has like the definitions and theorems and corollaries and stuff like that. And it has each example, but it doesn't have the answers to the examples, right? So the suggestion is to go through in advance and see, can you work these examples on your own? And then when we meet, we fill in the gaps. And so when I load a copy of these notes at the end of class today, you'll have the instructor notes, right? So you have all the details, all the results for each example. And so, yeah, I'll be loading the notes at the end of each session, and it's going to be in one location. What was the other thing? It was the notes. I kept trying to say it. It's not the exam. We talked about that. It's not the notes. Oh, and then just be sure that, you've been, not only have you been doing our assignments in Pearson, so that's my math lab. You access it through Blackboard. There's no course ID or anything like that. But also we have a lab component. So, that's independent of Pearson. So, that is run by Dr. Lamar, facilitated by Dr. Lamar. So hopefully you've been in communication with her and following her instructions, okay? All right, so with this example, write a linear function where g of 1 is 4 and g of negative 3 is negative 2. So if we're working with the linear function, it's a good idea to use the model, right? So you have this f of x here. Before that, we had these two pieces of information, right? It says g of 1 is 4. So that means that when x is 1, y is 4. And then it's also saying that when x is negative 3, y is negative 2. If it wants a linear function, then it's a good idea to use the linear model, which is f of x equals mx plus b. And then it looks like for this one, a good place to start would be finding the slope between these 2 points, right? So the slope formula is y2 minus y1 over x2 minus x1. Again, this is the slope between 2 points. Now, I'm a fan of whenever I have set of ordered pairs, I like to just automatically label them like x1, y1, x2, y2, right? And I think that's all the necessary preliminary information that we need to answer this question. So let's go ahead and find the slope between these 2 points. Our y2 is -2 minus y1 is 4. And again, this is giving us our slope. Our x2 is -3 minus our x1 is 1. Okay. On top, we get -6. On bottom, we get -4. This reduces down to 3/2. Okay. So I'm a fan of taking this information and one of our points and plugging it into this y equals mx plus b. I feel like that's more simple than other routes. So I think I want to work with that first point. That looks like it's going to be easier to work with than the second because there's no negatives. So then when x is 1, so we have 1m, which is just m. Wait a minute. Sorry. So let me see. The slope, we found it to be 3/2, so we have m. I'm choosing that first point, so x is 1, okay? B is what we're trying to solve for, and the corresponding y should be 4, okay? I'm going to continue working over here. So then if we solve for b is going to be equal to 8/2 minus 3/2 to give us 5/2. I basically subtracted the 3/2 from both sides. So it's 4 minus 3/2, but I rewrote it so they had a common denominator. Okay. So then for our y-intercept, we got this. For our slope, we got this. So then if we put those two pieces of information together, our linear function should be 3/2 x plus 5/2. Okay. So, before we move on, we want to ask ourselves, well, does this answer make sense? Or what does this mean for this to be the answer? All right, let's copy. So in order for this to be the answer, we're saying that when x is 1, the corresponding y is 4. When x is -3, the corresponding y is -2. Okay. So then, just a quick check, right? So when x is 1, 3/2 plus 5/2 is 8/2, which is 4. So that one checks out. When x is -3, you're going to get -9/2 plus 5/2 is a -4/2, which is -2. So this one checks out as well. Ooh, sorry, guys. I know every time I get to you guys, I'm like, my energy is so low. It's just because it's so late in the day. It's so weird. It's just weird. Like I don't know. That's why I was so excited about this, doing something different with the last group. Because it just woke me back up. Let's see. We got 3/2 x plus 5/2, and we confirm both the numbers that they work. You see it here. Let me just check the chat really quickly. Chat looks good. Okay. Let me get a volunteer to read this slide for me, please, and thank you.
I'll read if no one wants to read.
Okay.
Increasing, decreasing, and constant functions. Let f be a function and let x1 and x2 be any two numbers in an open interval a, b, containing the domain of f. The symbols a and b may represent real numbers, negative infinity or infinity. Then
the following is the case, right? Let's recap really quickly. Let f be a function and let x1 and x2 be any two numbers on an open interval a, b contained in the domain of f. Then the symbols a and b may represent real numbers, negative infinity or positive infinity. Then we have the following. We say that the f is going to be an increasing function on an open interval a, b if when x1 is less than x2, that implies that f of x1 is less than f of x2, all right? So what that's really saying is, in a graphical sense, as we trace the graph from the left to the right, it's going to go up. So notice x1 is less than x2, the corresponding f of x1 is less than f of x2, right? So in other words, as we trace the graph from the left to the right, our graph is increasing or rising on this open interval, okay? So if that's an example of increasing, then here we have decreasing. So we say f is a decreasing function on the open interval if when x1 is less than x2, that implies now we have f of x1 is greater than f of x2. In other words, as we trace the graph from the left to the right, our graph falls. All right. And I feel like this technical definition is a little bit of a challenge to digest, but just basically as you trace the left to right is going down, that's a lot more simple to digest. And that's essentially how we're going to be using it for our context. We're not really going to be using this too much. That's just there so you have the backstory. And then so you can have a complete idea or whatever. F is a constant on the open interval AB. If when x1 is strictly less than x2, that implies that basically our corresponding y values are equal to each other. So in a graphical sense, when we trace the graph from the left to the right, it stays flat, or it stays horizontal or flat, which is constant. Okay. So I feel like let's look at this in action, and I feel like it'll become more clear. So from the graph of G, find the intervals over which G is increasing, decreasing, or constant. So as we want to start from the far left, right? If we're going to the far left on the x-axis, how do we capture that? What is that called? What symbol is that?
Far left to x-axis?
Huh?
Negative infinity.
Right. So as we go from negative infinity, now the first change occurs. What's this x value here?
That x value is -2.
-2, right? So that's our first. So now as we trace the graph from negative infinity up to -2, is our graph increasing, is it decreasing, or is it staying constant? Is it going up, is it going down, or is it staying flat or horizontal?
It's going horizontal, so that means it's decreasing, right?
Are the y values going up or down as we trace it from the left to the right here?
The y constant going up, right?
Yeah. So as we trace it from the left to the right, our graph is going up, right? So we say it's increasing on this open interval. I'm going to abbreviate increasing like this. So we're saying that it's increasing as x goes from negative infinity up to -2. So then the next set is as x goes from -2 to what is this? As x goes to 3. So what is our graph doing? Is it increasing, decreasing, or staying flat or constant between these two x values?
Staying constant.
Staying constant, right? So as x moves from -2 to 3, it's staying flat. Now, as we do increasing, decreasing, and constant, it should be parentheses the whole time. Okay. And then the next checkpoint is as x basically on the right-hand side of this 3. So to the right of 3 here, is our graph increasing, decreasing, or constant?
Decreasing.
It's decreasing. As we trace it left to right, it's going down, right?
So
Go ahead.
So you for this tracking behavior of the function, you have multiple intervals between each point. So like from that left arrow to the -2 to that's one interval.
Yep.
Then that point to 3-2.
Yep.
And then 3-2 to the next arrow.
Yep. It basically those two turning points breaks the x-axis up into 3 segments. You got region 1 over here, region 2 in the middle here, and then region 3 on the right.
Okay.
And so region 1 is increasing as we trace left to right. Region 2 is flat, so on and so on. Okay. Yeah, that was good, right? So we said it's increasing as x goes from negative infinity to -2. is staying constant or flat as x goes from -2 to 3. And then we said the function is decreasing as x goes from 3 to infinity. So notice all of these are going from the left to the right. And then you can see a type version of those results here. Increasing here, constant here, decreasing here. Okay, can I get a volunteer to read this slide for me, please?
If A is the domain of this function f, we say that the value of f of A is relative minimum of f if there is an interval x1, x2 containing A such that the entire thing or just that part.
Keep going.
F of A is greater than or equal to f of x for every x in the interval x/x2. We say that the value of f of A is relative maximum of f if there is an interval x1, x2 containing A such that f of A is greater than or equal to f of x for every x in the interval x1, x2.
Okay. So, and just here, less, I think you said greater than twice, but it's fine. You got it correct here.
Yeah.
So if A is in the domain of a function f, we say that the value f of A is a relative minimum. Okay. So relative minimum is basically like a valley, the bottom of a valley in our graph. So in a graphical sense, it's saying that the y value corresponding to the A is going to be less than or equal to all nearby y values. So it's going to be like in the bottom of a valley for every x in that interval. And then we say that f of A is a relative max of f, basically if that y value corresponding to the A is greater than or equal to all nearby y values for every x on that open interval, right? So in a graphical sense, I feel like the graphical representation is the easiest way to grasp that. Here are two examples of relative minima, the bottom of valleys. And then here are two examples of relative maxima, the peaks of the mountains. All right, that's what the text was saying, describing these points here. So then here we have a slide on what do we mean by a function being even. A function f is called an even function if each x in the domain of f, negative x is also in the domain of f, and we have this to be the case, all right? Whenever we evaluate f of negative x, we get back to the original. So then we say the graph of an even function is symmetric with respect to the y-axis. What does that mean for the graph to be symmetric with respect to the y-axis? Or what does it mean for anything to be symmetric? What does that mean? Symmetry. Or can you give me an example of things that are symmetric?
And they just parallel one another, or
yeah, like can you give me an example of something tangible that behaves that way?
A mirror, I guess. I don't know.
Okay, like the typical mirror, right? You can cut it in half,
right.
And like I don't know, well,
I was thinking more. Yeah, like when I was thinking more like the transverse. So yeah.
Okay, so like for instance, basically what it's saying is like if you have a graph. So when something is symmetric about the y-axis, you can cut the graph along the y-axis and one side is going to mirror the other one. I realized as I went to explain it, that's how you meant to use the word mirror, but I was talking about a mirror, but you were talking about one side reflecting the other, which is totally fine. But yeah, so a function being even means that it has y-axis symmetry, which means you can cut it along the y-axis and one side is going to match the other or mirror the other. Now, algebraically, to determine whether a function is even, we evaluate f of negative x. If we get back to the original, then we say the function is even. It's going to have y-axis symmetry. So if we could talk about a function being even, then your intuition would say, what? We can also talk about a function being what? If it's not even, then it might be what?
Odd.
Odd, right? So what do we mean by a function being odd? A function f is an odd function if for each x in the domain of f, negative x is also in the domain of f, and we have the following. So whenever we evaluate f of negative x, we get negative times the original. So when a function is even, f of negative x produces the original. That means the function is even. But when f of negative x produces negative times the original, then we say the function is odd. So in a graphical sense, the graph of an odd function is symmetric with respect to the origin. And so what that's going to look like is kind of like an S kind of thing, where if you were to cut it in half along the x-axis, put your thumb on the origin, and you rotate the top half by 180 degrees, it's going to match the bottom half. Another way to kind of conceptualize that is whenever you have x comma y, you also have negative x comma negative y, right? But the main point here with this presentation, an even function means when you evaluate f of negative x, you get back to the original. An odd function means when you evaluate f of negative x, you get negative times the original. Okay. So with this next example, let's see if we can identify these functions as either even, odd, or neither. All right. Okay. Home stretch. Solid 10 minutes, a little over 10 minutes. I'm totally asleep. Like I'm sleepwalking right now. I don't know why. I just get so sleepy by the time I get to you guys. I be like, I just want to lay down and take a nap. But it's okay. We got to bring the funk, right? Bring the power. Okay. So when we want to test for even, odd, or neither, what we want to do is basically replace each x with negative x, simplify, and then interpret the results, right? So if we're going to, for part A, if we're going to replace each x with negative x, when I do substitutions like that, first thing I like to do is replace each x with a blank set of parentheses. So we have g of x equals x cubed minus 4x. Again, I replace each x with a blank set of parentheses. And then basically here, I want to substitute in negative x. So I'm replacing all my x's with negative x. Man, that just sounds like a super scary time, a negative x. It's already an x, so it's gonna be one thing, but then she's negative or he's negative, that's gonna add to the whole thing. That's the spin on words. Okay, so let's simplify this, right? With this first term, we have negative x times negative x times negative x. Will the final result be positive or negative?
Negative.
Negative, right? So if we have an odd number of negatives being multiplied, the result's going to be negative. So this is going to be negative x cubed. But the second term, we essentially have a double negative going on. Negative 4 times negative x. What happens there?
It'll be positive.
Positive, right? So then, is this the original? This negative x cubed plus 4x, is that the original? No, right? So let's try factoring out a negative 1. If we factor out negative 1, we're going to be left with x cubed minus 4x. Is this negative times the original?
Yeah.
This is negative times the original. So then basically we get g of negative x equals negative times the original. And that's the definition of a function being odd. Let me just move this around to make it look a little bit more presentable. So that's the definition of a function being odd. Hopefully that's not too small. Okay, so then let's try part B. So we're doing the test for even, odd, or neither. We replace each x with negative x. First, we're going to replace each x with a blank set of parentheses. And then we're going to plug in negative x into the blank parentheses. And then now we're going to simplify. So if we have negative x squared, is this result going to be positive or negative?
Positive.
Positive, because we have an even number of negatives. So that's going to be positive x squared. The 5 doesn't change. Is this the original?
Yes.
It is the original. So then that means it's what?
Even.
It's even, right? That's the definition of it being even. When you have, in this case, we have f of negative x equals the original. So then that's the definition of it being even. I did not take college algebra before I got into grad school. I knew how to do algebra. I had never seen this concept of a function being, I thought a function being even, odd, or neither was based on the powers. I got into grad school and the teacher wouldn't just tell me, no, that's not the definition. They just let me be wrong. And I don't know why it never dawned on me. But I had never taken college algebra. So, college algebra has a lot of like simple concepts, but if you've never seen it before, you wouldn't even know to think that way. I started off in like calculus and I know how to do it, but I'm like, there were just a few concepts that I was missing. He could have easily just told me. I was just like, so I didn't realize it until I started teaching it. I was like, oh, that's what he was talking about. So I was like, I was still a little bit peeved about it, but it's, that's the long and short of there. Okay, so let's try part C. Do the same thing. First, we're doing a blank parentheses. Okay, I'm kind of out of space. So I'm gonna give myself some space. I'm gonna replace each x with negative x. Let me move this around so this looks a little bit better. I'm just gonna work here for now, and I'll read it. Okay, so if we focus on this first term, will the result there be positive or negative?
Negative.
Negative, right? Okay. 2x cubed. What about the next one?
Positive.
Is this the original?
No.
Yep. No.
All right. Look at that negative. If we factor out a -1, can we get negative times the original?
No.
Oh, that doesn't work either, right? So this is an example of something that is neither even nor odd. It's neither.
So if it's not the original like even, and if we factor out the -1, then it's neither, like guaranteed.
So when you get to that line, if it's not the original, then you, like you say, try factoring out the -1. Then you want to ask yourself, can we get to negative of the original? If you can't get to the original or negative of the original, it's going to be neither.
Okay.
And let me just highlight these. So we got odd, we got even, and then we got neither. That's fine. Okay, so let me get rid of this. Odd, even, and neither. Okay. All right. So then we have this piece on piecewise functions. So evaluating a piecewise function. Let me give a little bit of backstory. So a piecewise function, all it is several graphs on the same Cartesian plane. All right. So when you start graphing piecewise functions, you just graph them like normal, but then get rid of the part that you don't need, because each graph is going to be restricted to some portion of the domain. So again, you can graph them like normal, but then get rid of the part that you don't need. Okay, that's the simplest way I could think to conceptualize piecewise functions. So then this is kind of walking us through how to evaluate a piecewise function. So to evaluate f of a for a piecewise function f, determine which line of the function applies to the number a, and then evaluate f of a using the line chosen from step 1. All right, let's see it in action. It's not too bad. So in this example, for instance, they want us to evaluate when x is 0 and when x is 2. So when x is 0, do we use line 1 or do we use line 2? When x is 0, do we use line 1 or do we use line 2?
F is 0, use line 1.
Use line 1. Why are you saying use line 1?
Because 0 is less than 1.
Because 0 is less than 1, right? So because 0 is less than 1, then we're going to plug it in here. So then 0 squared, that result is 0. So then intuitively, when x is 2, we're going to use what line?
Second one, line 2.
We're going to use line 2 because 2 is greater than or equal to 1. If we plug in 2 here, I think we get 5. So 0 produces 0 there, 2 produces a 5 here, right? And you can see it typed out here. Okay, let's see the time. We got a solid 5 minutes. Let's see what else we got. I'll go ahead and do that. And I didn't get a chance to do this with any of my other students. We ran out of time. We can take some time to go through this one. I'm going to do a rough sketch though. Yeah, I'm just going to do a rough sketch just because we're short on time. So say this is my positive X. What is this? Cool, there's a ruler. Oh, and you can draw lines on it. Oh, and duplicate. Okay. But no, I'm not going to subscribe for. It's $11 for the year and then $12 for the year. That's weird pricing. But that was kind of cool. Say this is my positive X in this direction. And okay, we can kind of need a little bit more space. Let me about like this, I think. And we'll let this be our positive Y. And again, this is just going to be a rough sketch. So a lot of this is centered around when X is 1. I think they call that like they had a name, I saw it somewhere, but we're focused on when X is 1, right? So for instance, if I graph the first one like normal, I'm just gonna graph it like normal. So say this is like 1, 2, 3, 4, 5, 6. And again, I could do graph paper. I'm just trying to be quick. This is my origin. If I use graph paper, it would be like, it would match up. 1, 2, 3, 4, 5, 6. Hopefully this is large enough. 2, 3, 4, 5, 6. Okay. So for instance, let's do the first one. Anybody got a favorite color?
Red.
Orange.
Okay, I heard red first. We'll do red. A lot of men choose red. It's a very like power color. Okay. So let's do that one in red. All right. So if we graphed it like normal, the y-intercept is 1, so we can put a point there. And then the slope is -2. All right. So back one, like a point here. I'm gonna just connect those with a straight edge. Let's do it like this. Okay, we get something. Let's see if I can get this to work. It is decent, right? That's close enough. All right. Okay, we're gonna come. Let's go ahead and make the change, right? But it says that this graph only applies when X is strictly less than 1. So we need to kind of be focused on this guy right here. And let me do some changes. Style. Let's do like this. Too thick. All right. So that's our look. That's what we're focused on, right? Because everything happens around X equal to 1. So this one says this only applies when X is strictly less than 1. So what we got to do is get rid of part of this. I see the time. Thank you. I want to do a partial erase. That's good. All right. So we're keeping it to the left, and then we also need an open circle here. That's good about there. Let me do style, fill. Maybe fill it like that. That is, let me see. When X is 1, we should be at -1. So I kind of need to move this around a little bit. So see, that's what happens when it's not drawn to scale. It gets off a little bit. So instead, what I'm gonna do, I should have just put it on some graph paper. I'm gonna just kind of move this down a little bit. It's just off because I'm not on graph paper. Okay, but that's essentially it. Can I cut this? Let's see. Cut, paste. I'm getting you guys out of here. Yeah, that's what I want. Okay. So for the first line, I graphed it like normal, but then I erased the right-hand side. And I used an open circle because there's no bar here, right? It's strictly less than 1. So the open circle means you get close to it, but you don't include it. For the second one, if I graph that one like normal, anybody got another favorite color? Okay, I think I heard blue. Copy, paste. Style, blue. We'll do that one in blue. So the y-intercept is 1, the slope is 3. So when x is 1, we're at 4. This is like here. Why does it look crooked? Is that crooked? Now it's not letting me move it. That's fine. So I think that's filled in, and then the slope is 3. So we're kind of out of space. 1, 2, 3 is about there, and 1 is about like here. So it's kind of like this. And again, if I was drawing on graph paper, it would be better. All right, but I used a solid circle there because you have a bar here. So I used a closed in circle. And again, I was graphing this like normal, but I got rid of this part going off to the left because this only applies when x is greater than or equal to 1. So for the red, I kept the left-hand portion of the graph. For the blue, I kept the right-hand portion. And then that's the graph of the piecewise. And then you can like get a few additional points, like, you know, like consider when x is a half, when x is a -1/2, -1, -1.5. And then maybe when x is 1.5, just choose several values of x. You can plot them and, you know, but the main idea is you graph like normal and then just get rid of the part that you don't need because of the restrictions of the domain. So that was a quick demo on us doing it by hand. And then if we compare it to the prepared notes, you can see it here. All right, and you see the final result to the far right. Are there any burning questions before we go our separate ways? Any burning questions? Okay. If there aren't any, let me check the chat really quickly. Okay, the chat looks good. So, and let me go ahead and load a copy of this presentation so you can see the PDF in our box folder. And again, I'm putting all of the PDFs for all of my classes in the same folder, so you can actually pull the notes from my other sessions as well. And you can watch those recordings because I usually put the video recordings in the same locations. Okay, so if there aren't any burning questions, we're going to end the session here. And from one beautiful mind to another, enjoy the rest of your day. Take care, guys. Peace.
Take care.
Take care, sir.